TGA stands for thermo gravimetric analysis. Usually when we've got a 3-letter acronym for one of our techniques, we don't include words like analysis or, that's more generic. But I think they probably just didn't want to call it TG because that has its own things in the world.
Yep.
So thermogravimetric analysis. Any breakdown of those words that you recognize?
Thermo, heat, and then gravimetric, something to do with gravity.
Yes. Gravi being like a weight related thing. Metric meaning measure. And then we're going to ignore analysis because we all know that analysis is just a word. So this is the study of how heat and weight affect one another. There's usually a first thought that pops into people's heads when it comes to how heat and weight affect each other. What is your first,
Heat changes density.
Heat changes density. Does it change weight though?
No.
So the weight stays the same. That's a volume change. And there is a technique called dilatometry. That is going to measure size and shape change with temp. So that would be better for studying like a density change. Thermogravimetric is looking at weight change. Any other thoughts on weight change with heat? I can also just say it.
Things off-gassing.
Things off-gassing, yep. So we can lose weight or lose mass. I should probably be writing mass because this is a scientific endeavor here. And that would be like off-gassing. That could be volatilization, which is off-gassing, but said slightly differently. We can also get like boiling or evaporation. Again, off-gassing, but with a more specific route. Also, we can get, if we are doing a reaction where gas is one of the products of the reaction, that would be evolved gas, and we'll call that EGA, evolved gas analysis, because in this technique apparently we really like sticking the A on the end for analysis. An example of such a reaction would be baking soda to,
Baking soda and
baking
vinegar.
powder to baking soda. So baking powder we have in our kitchens. Baking soda is one of the ingredients in making detergents. So if you're like a person who likes to make your own detergent at home, or there's a couple other uses for baking
powder.
Sorry.
I thought it was soda that you use.
Baking soda to washing soda. Is that what it's called? I know the chemical interaction.
Yeah.
I think it's called washing soda, actually. Or washing powder, I don't know.
It's just sodium bicarbonate, but in a different form, or?
Washing There we go. Okay, it is washing soda is what it's called. I apologize. So turning baking soda and baking soda, I've got that written down. NaHCO3. That is baking soda. I'm gonna write it down because apparently I'm getting confused about which one's which. And if you heat it up, you get washing soda. This is what's used to make detergent, washing soda here. It's sodium carbonate, not sodium bicarbonate. And you also get two gases evolving, well, two byproducts, both of which, if you continue to add heat, will be gases eventually. Carbon dioxide starts as a gas, and you can also evaporate off the water to dry it off entirely. Mm-hmm. So studying this reaction in a TGA is going to show you these two gases. And I've done it several times. You actually can calculate the mass of these two constituents that are going to evaporate off, and you can relate it back to the mass of beginning. You can
ice tables, like, go burr.
Mass, do what?
Ice tables.
Ice tables?
Yeah, initial change, final. Well.
Oh.
Yeah, ice tables. So you say, oh yeah, the initial mass is this, then the change is this, and then the final is this. And so you can calculate the initial reactants.
Yes. Yes, it has been a long time since I thought of the acronym. Cool. Yes, ice tables. So it's fun to see something as like you can do this in your kitchen at your house. And it's fun to see something as simple as this and accessible as this in a TGA. Very straightforward chemistry. Probably should change that to gray or something so it's not too everything's black. But anyway, a common use for evaporation, why we maybe would want to study boiling or evaporation, would be water content. So I can figure out percent of water in a material. Say I've got a hydrogel that is partially hydrated, fully hydrated, mostly dehydrated. I can figure out what percentage of water is present in that hydrogel by evaporating or dehydrating that water, that sample. Okay. Another one that we don't talk as much about is gaining mass as heat is related. Can you think of any examples where that happens?
It absorbs things from the air. I'm assuming this is an open system, not a closed system.
It is, yes. It's sort of a combination between the two. It's a controlled system, but yeah, generally an open system. What kind of things might we absorb out of the air? There are two really big ones one that we see out in nature, and
oxygen.
Oxygen. So oxidizing
and then
often works better at higher temperatures. So it's the conversion of iron to iron oxide, and there's various forms of iron oxides.
And there's nitration, but that's super, super high temperature.
You can get nitrogen uptake. More commonly, you're going to get carbon sequestration, so carbon uptake. That's actually a really big study right now as we're trying to fix the climate, is how do we fix carbon into a solid form instead of letting it bounce around the atmosphere. And both of those are going to be dependent on atmosphere, the surrounding gas. If I'm running my TGA test in pure nitrogen only, neither of these is going to happen. Atmosphere or environment specific. So we can choose which gases are flowing over our material in order to get the weight, the mass loss or the mass gain that we are interested in studying. The typical setup for a TGA is actually very, we could call it low tech. It is essentially a scale inside a furnace. So usually what we do is we have some like transducer up here, basically just like a weight scale. It's got a big long bar hanging off of it, and then we hook this little like bucket, and it's really a very small bucket, usually around the size of like a hole punch is its like footprint. You could go bigger if you wanted to, but often we don't need that much mass to like to be able to read things properly.
I'm assuming it's shielded because heat does mess with scales like that. Most scales.
Yes. Yeah, so there'd be like a seal right here. I probably would draw that smaller.
Or an Atwood machine. Have the thing pointed sideways and off to the side.
So we're going to talk about that. So that's the higher tech kind of version. Takes a lot more effort to have the weights sticking out to the side versus dangling down. And we're going to talk about both. So we have this little seal and then this big old furnace. I'm going to actually draw the furnace in red because red means temperature. And the furnace is usually big enough that we can fully surround the sample. Often the furnace can raise and lower.
So you can do heating and cooling cycles?
The furnace would raise and lower so that we can put the sample in and out. You could have a door kind of in the front of the furnace as well. Just a couple different ways we can set the thing up. If there is cooling, then part of the furnace would be some tubing or fans or something so that we could blow cold air or even like flow liquid nitrogen through the system to get significant cooling. Depending on the upper range of the furnace, there might not be any cooling elements. Generally in furnaces that are going to be heating above 1,000 degrees Celsius, so ones that are really good for metals or ceramics studies, they don't tend to include a lot of cooling elements, maybe a cooling fan. But at those temperatures, we're so high above room temperature that they're going to cool down to room temperature fairly quickly on their own. They hold all that thermal heat and it dissipates fairly quickly. In those instruments where you're having to do metals and ceramics, we don't usually care quite as much about the below room temperature measurements. However, if this was a TGA specifically for, say, polymers, where we maybe did want to see something as it sits in a freezer and then slowly bring it up toward room temperature and we expect maybe volatilization in that range, then it would focus more on cooling strength and less on heating strength. So it doesn't usually have everything. You kind of select what you're interested in.
Because generally people don't do both, and so the machines that do both are expensive and not very many people make them.
And
So they're
not
like,
a lot of
why
people even need,
why get it when you don't need the option?
Exactly. Even in our lab, where we are a generally accessible research space that does testing on behalf of a ton of different projects, we just have two different instruments. We have an instrument that goes cold and we have an instrument that goes hot. And that they can both be sensitive in their kind of line of work. I don't have to worry about having one instrument that covers everything. We're actually going to talk in a minute about how combining instruments has some pros but also has some cons. So sometimes it is better to just have an instrument that specializes. So some benefits to this kind of setup. I am using gravity for my good. The scale or the sample itself is unlikely to swing back and forth because I have gravity just pulling it straight down. So gravity is my friend. This is also scientifically a very simple setup. Furnaces are easy to repair and replace. Scales are easy to work on or replace. And then this big long arm is literally just a piece of usually like alumina or some strong material that's not gonna like give much. Yeah. So like all of these parts are very simple and easy to replace should any like repairs be needed. So easy repairs. And I like, personally, I like things that are simpler in technology because they are easier to understand as well. You can look at this and be like, ah, yes, that's pulling on the scale, so it's going to measure its mass change. And as the person who tends to fix our instruments, it's a lot easier to diagnose something with really straightforward physics.
Yes.
So this is like, it's a great setup. Some of its struggles, and I'm becoming aware that the orange and the red are just like painfully close in tone. That's fun.
Indeed.
The fun of living right in the path to the only road to the hospital. So some of the struggles here, you mentioned scales and heat are not great friends, and heat rises. So we do have the potential of messing with the scale if the scale isn't up high enough, or if that seal breaks down. We also don't really have, like, there is airflow considerations that have to be made. If I am flowing the air upward like this, there's a possibility that it'll push up on my scale, on my sample, and change what the mass looks like. But if I'm trying to flow air this way,
A little bit heavier.
Heat rises and it's going to continue up this way. So I'm not going to get, like, I'm going to get the air like spiraling in here instead of traveling all the way through. So there isn't a clear, like, starting to ending path for the gas. And you'd have to have a pretty solid flow to get it to go from top to bottom.
Why they have the interlocking key? Yeah, I said if you need a criminal act, you know who to call.
Alrighty.
Probably the camera again.
Nice.
I wonder if she wants to know that I'm recording or not.
To be noted.
I think I won't publish that bit.
Nice.
And then one struggle that's not really a struggle because it's not a struggle when we talk about other techniques, but we're going to talk about it today because the TGA instruments that we own in our lab space are combined with DSC. And I've already got a video about DSC that you can look at, like, exactly how DSC works on its own. But another struggle with this is it's hard to measure really anything else. I can't put additional sensors in here to measure other properties about the material. So
anything electric is heat sensitive. Yippee.
solo, this is very much a solo technique. And like I said, I maybe shouldn't put this under struggles, because when I talk about XRD or SEM, I don't talk about their ability to be hybridized with some other technique. I'm not like, this is a bad technique because I can't combine it with other things. The only reason we're doing that today is because, like I said, our instrument is a combo, and this is just going to help me justify a little bit why our setup is a little bit different. So we have the setup that you were talking about, where we go sideways. So we've got these long beam arms with sort of a flat, you could call it like a plate on the end. And the beam has a fulcrum, and then some additional, like, there's like a little weight back here. I'm gonna just copy that for a second because I'm gonna use it later. And I set my little crucible on the plate at the end. And I stick an electromagnet, which I'm going to draw just like a north-south magnet, because that's the easiest way to show. I stick a little magnet near the weight at the end. This is an electromagnet, not a like a rare earth magnet or something, which means that I can increase or decrease its magnetic pull depending on the current that I send through this.
So you have some position sensor in the electromagnet that it just kind of hovers it, and then you read the voltage that you're pumping into the electromagnet to see, oh, hey, this is how much weight is on the thing.
Precisely, yep. So what we are using to measure, quote, the weight, is how much work the electromagnet has to put in order to maintain this horizontal balance. If the sample loses weight, then this back part is going to become heavier than it, so the sample is going to move upward. And then the electromagnet is going to have to put through a little bit more current, voltage, etc., to pull the weight back up and maintain level. Same thing, if this starts taking in gas from the air around it, it's going to go down, the weight's going to go up, and the electromagnet is going to have to relax to allow this weight to drop back down toward horizontal. So that's how our scale works in this situation here. And what's nice about this option is I can stick the furnace over here, and now the furnace can move this direction. So we are now in the horizontal instead of the vertical plane. I can have a gas flowing this direction, and I don't have like gravity considerations. There are some weight considerations, which I'll talk about that in a second. I'm not going to call it N2, although we do normally run in nitrogen for just a lot of the work that we end up doing. This would be purge gas. So we've got our purge gas flowing over, and then our furnace can close over top of the specimen. And same thing, if you've got like a fan or liquid nitrogen, you could also incorporate that into this. The benefit and the reason why our instrument has it is this is more of a combinable. There's got to be a better English word than combinable. Can be hybridized. And we're going to talk about how it's hybridized for our instrument. Gas flow direction is a lot more simple. And the scale or the electromagnet can be fully shielded from the heat, and we don't have to worry so much about like the hot air rising up toward the scale. So the scale is protected from the heat. We're pretty much doing exactly opposite of the struggles and benefits though, because in this situation, I am working against gravity always. Gravity is constantly going to be trying to pull one side down over the other. So I have to pay attention to how my balance is when things are just like empty. It's not particularly easy to repair. This is a very delicate balance right here. And there's a lot more electronics going into this setup. I can't just like swap out the mass measurement tool. There's all sorts of bits and pieces. And then it's a little harder to diagnose because there are physically moving parts, there are electrically moving parts, there's, you know, a lot more to it, so. Struggles, gravity.
Does the main like data processing happen at like the board that has the electromagnet control board, or does it just say here's what voltage I'm pumping into it, and then it just has something that makes it just work right? Like it has the sensor and the magnet are integrated, and it's just like a PWM circuit.
I don't know the details of our circuitry. I do know that as far as what it gives to the computer, it reports both the voltage values, so uncalibrated, just like raw values, as well as calibrated weight values. So it does some conversions. I don't know whether it's the software doing the conversion or the board at the instrument. Everything kind of talks to each other, so it's hard to know where any of that originates on ours.
Fun.
And I have relied on qualified technicians to do some of our board replacements over the years as we've needed them. So I haven't had to, other than checking like, do we have voltage between these two nodes? I haven't had to do any significant
Like repairs.
Repairs on the boards specifically. On the beams, always. On the weight balance, absolutely. I've had to do a little bit of diagnostics on our furnace as well. But the boards underneath everything, I don't think I've really done that much with them.
Yeah. It would be that hard to tune it, but painful.
And it does, like it has all sorts of tuning capabilities on this backside over here as far as where is zero, where is horizontal. And that's part of replacing this beam, because try as they might, some of these beams are going to be a little bit heavier or a little bit lighter. So this weight actually can move, on our instrument anyway, the weight can move out and in to balance this side. And then there's also a chip that you can move up and down to reach that kind of balance point. So those kinds of things they build in to be very like user accessible, because they know this balance is so sensitive that we are going to need to check it and recheck it and recheck it, and we don't want to send out a technician or get a technician in every single time we have to do that.
Yippee.
One of the big struggles that we get with this setup is called the buoyancy effect.
Because it's a mass on a scale, when there are sudden weight changes, they happen super slowly.
They can. The buoyancy effect, when we're talking about this here, actually has to do with this gas flow. So if you imagine, I've got my furnace here and I've got my cup out in the middle of the furnace. And I start, and the furnace actually has this little like cone shape at the end so that the gas doesn't backflow into the backside of the furnace. I think that's a cool little feature of it. So let's say I've got nitrogen, and at room temperature, the nitrogen is just like kind of consistently flowing through and then out. When I start to heat up the furnace, it's going to be the walls. This is a tube furnace. So I've got it looks like a little like ceramic pipe that's actually providing the heat to my sample. So the walls, the floor, the ceiling are going to be what heats up first. What does gas do when it heats up?
It decreases density.
Decreases density and therefore tends to travel upward. What this creates is areas of low gas density. I'm actually going to write that in gray. And in the center is probably the coolest, so we're going to have the highest gas density. And it's not going to be like crazy high, but it is high relative to the stuff that's being heated right at the walls.
Mm-hmm.
The stuff at the top is low density, and it's on top of the high density stuff. So like this setup, the top half is just fine. Everything's really stable. But this higher density gas is going to want to travel downward, and at the bottom, the low density gas is going to want to travel upward. So what we end up getting is only in the bottom half, we get this sort of circular as gas heats and cools, and it's minor. This is the biggest difference when we like turn on the furnace from 0. Like if I start at room temperature and then I'm like, ready, go, it's the most obvious right in those couple of moments at the very beginning. But because I have this moving gas, do you know how airplanes work? It
Creates lift when it's moving.
Creates lift when it's moving, yep. So we have all this moving, bubbly gas going on down here, and our sample is going to appear to lose mass right at the start of our test.
So you use the temperature sample like a couple seconds after that happened, the weight measurement, so that you can just like say, oh yeah, all that stuff was just bad data, and we start here.
Yes, so that is, the people ignore the first several minutes of data. The instrument will show it to you, and you can be like, ah, yes, look, the buoyancy effect. Things are going weird for a second. It's usually not a big deal. Let me write out what the buoyancy effect is. Gases rising and falling on lower half of furnace creates lift on beam on. Worst at beginning of test. After this point, the electromagnet can usually compensate. We get a kind of uniform like flow of gas. This stabilizes into like, oh yes, we are constantly doing this.
There's just a force upwards.
And yep, and the electromagnet can balance for that, and then we reach kind of where 0 is, and that's going to work just fine. So that's why it's the worst at the beginning of the test, is the electromagnet just hasn't quite caught up with it. This is going to be the biggest problem for low mass. How do I write this? More prominent. I'm not confident that's how to spell prominent. So you can imagine if my arm is just like I'm like lifting my arm out into the air, and my shoulder can be pretty relaxed, and if like someone comes and like high fives my hand, it's gonna swing my arm, right? Because I've got a nice relaxed shoulder. Now let's imagine I've got myself braced and I'm holding a bunch of books. Someone high fives my hand or the books, I have a lot more mass. Even if they high five fairly hard, they're not gonna move my hand nearly as much because I have the mass advantage in this situation.
They're applying a force, and it's force equals mass times acceleration, so it's force divided by the mass that you're trying to accelerate.
Exactly.
The acceleration.
And I have the mass advantage.
So
So in this situation, if I have an empty beam, then the buoyancy effect is going to be a real problem. If I have a beam loaded full of sample and crucibles, and that's going to be several 100 milligrams worth of mass, which doesn't sound like a lot, but compared to the lift that's happening here, is significant. We're going to have less of a problem. If it's a significant problem, if someone has like a really fluffy sample, putting a lid on the crucible can help, because you're just adding mass to the situation. You're gonna get less lift. So best way to fix that is to use at least 10 milligrams of material, possibly use like a lid just to weigh everything down a little bit more.
10 grams?
Milligrams.
Oh, milligrams.
Remember, we're working with a crucible that's about the size of like a hole punch.
Oh.
Tiny, tiny little things. We're measuring everything in milligrams. We use alumina crucibles, so they're a ceramic crucible that are stable up to very high temperatures.
The little white ones.
Tiny little white ones, yep. And they can hold 90 microliters, which for a lot of our powders, 10 milligrams is a good fit in there. Some people do more, some people do less, depending on the density of their material. So 2 ways to fix the buoyancy effect. One is heavier crucible or sample. About 10 milligrams of sample. The second way to fix it is to calibrate, and we always do a weight calibration. Especially when we've just replaced the beam arms. But a weight calibration, we do 1 empty and 1 weighted. And it knows what it knows that it's empty when it's empty, and it knows that it is weighted with a specific weight when it runs the weighted version. So it knows what it should be reading, and it can calibrate to those. So that's 2 ways that we can kind of minimize the buoyancy effect. This weight calibration has a secondary really useful thing. Thermal expansion. I should probably have talked about thermal expansion a little bit up here. I mentioned that this arm right here is alumina, and you mentioned creep. I don't want something that when I heat it up is going to elongate slowly over time. But everything, even if it's not going to creep with the weight, with the heat change, everything has some thermal expansion. It gets hotter, it gets longer. We talked about that up here also with dilatometry. In this setup, a longer beam arm makes no change to the scale. Because that change in length is a change in density, it's a volume change, and it's not a mass change. The scale here does not care. So I probably should have added that to my benefits of this one is thermal expansion.
Oh, I see how it affects the other one. 'Cause
No
the,
issue. Yeah.
The rod expands and it creates a longer fulcrum.
Precisely. So on this one, if the beam gets longer, it's going to look heavier to that electromagnet toward the back. Heat makes the beam expand. Longer beam equals, we'll say, equals tilt on fulcrum. Tilt is read as weight gain. Oop, there we go. So the weight calibration serves sort of this dual purpose, where the weight calibration is going to also zero out that thermal expansion, because the instrument knows when it's running this weighted test here, it knows that it has a constant weight. And so any expansion or any increase in that weight that it reads can be zeroed out, essentially. This is where I was talking about the instrument reports voltage values to the instrument, especially when we're in a calibration mode. It reports just the raw voltage values so that we can double check that it's reading proper raw values, and then it converts that into a weight. So when we calibrate, we are calibrating the electromagnet, and then we turn that into a weight calibration.
Yeah. They probably have it current limited, and that's probably how they tune the electromagnet, because its current is proportional to the amount of force applied by the electromagnet. So.
Yes. All right.
Yippee.
We are going to talk about, let me just double check. Yeah. So we're going to talk about ours as a combo instrument. Most people, this is not going to make a difference to them, because if you have a standalone TGA, no matter which orientation, whether it's this one or this orientation, not all TGAs are going to be combo instruments. But ours is, and so you need to understand the combo instrument situation. Is there an easy way for me to paste? I don't know. Not sure I'm the biggest fan of this situation. This is why I copied my beam arms earlier. Is because our TGA, instead of having just one beam, has two beams. And I am trying to draw a three-dimensional system in 2 dimensions. They are horizontal and parallel and right next to each other. So one, like if I were to draw that in like the 2 dimensions and I was looking at it straight from the side, it would look like this. Where they're kind of like right on top of each other. I'm going to draw us a little bit at an angle, like an upward angle, so that we can see what's going on both of these. Ours is a combination DSC TGA. We'll do that in purple. And we have the same setup where we've got our furnace. And the furnace can close over everything. DSC, and I have a whole separate video about DSC and the specifics of that. But DSC is, for us, it is a measurement of how temperature affects heat flow. And what I'm talking about there is when ice melts, that is an endothermic reaction, meaning heat is flowing into the ice to turn it into water. And that is a temperature-driven reaction. So that's when I say temperature versus heat flow. I'm talking endothermic, exothermic reactions, plus some other kind of expanded stuff. But DSC is really great at looking at things that absorb or release heat. And some things, like ice melting, have no mass relationship. There's no mass change when ice melts. Some things, though, going back to my baking soda, washing soda, here,
It is.
I'm adding heat and my mass is changing, and I probably absorbed some, or let's see, I'm actually not fully sure if that would be endothermic or exothermic. I would guess endothermic. But I've got some exchange of heat going on here. I apologize if I'm incorrect on that being endothermic or exothermic, but without Googling, we have the information that's in my head, and that's all. Stop that. DSC, the D in DSC stands for differential. So that means that I have to compare two things. What I'm comparing is an empty to a full. So I am comparing one pan that has nothing in it to one pan that has a piece of ice in it. Meaning that I have to have two beams in this situation in order to do any sort of DSC analysis. So in this setup, this combination DSC TGA, I have a reference beam. In ours and in most of the ones that I've seen, the reference beam is at the back. It's farther away from the user, because we're just gonna stick an empty crucible on there and we're gonna leave it alone. We're not gonna do anything else with it. So, and up at the front we have our sample beam. And that's usually gonna have, 10-ish milligrams of material. It might also be empty. There are reasons in DSC why we might want to collect two empty pans, sort of as a baseline, like a miniature calibration kind of situation. And I also need some way to measure the temperature and the heat flow at the sample. In TGA, I don't really care exactly the sample heat flow, so we just measure the temperature of the furnace. In this one, though,
Is there like a thermocouple in the
there
or
is
thermistor in
right
the
at the bottom here. The plate is covered with platinum, and then there is a platinum wire that is, in ours, it's encased in the alumina, and it then separates at the back and acts as my little thermocouple. And like I said, this is a platinum plate and wires. So I've added a little bit of complexity to something that was already, a fairly complex system with my electromagnet and all the boards and such. Oh, bummer that I'm like off the edge there. I don't like that. And luckily we're already doing all of this, like the weight calibration and things, because the platinum is going to have a different thermal expansion than the alumina. And the platinum expanding and contracting is going to change the way it conducts that heat along it ever so slightly. So we do have a couple extra calibrations that we do in order to make this system work. But this is what we actually have two combination DSC TGA instruments, and this is their general setup here. I don't think I've said it earlier, but our furnaces have a temperature range from room temp. I don't really trust them below 50 degrees Celsius, which isn't room temp, but like, here we are. And ours can go up to about 1500 degrees Celsius. So our combination DSC TGAs are high temperature, and that's specific to our lab. Different furnaces, different instruments are gonna have different ranges of temperature compatibility. So what are some like pros and cons of having a combination instrument? Any thoughts?
More parts.
Is that a pro or a con?
It's harder to repair.
Yes.
Because it's more fiddly. I'd say that it could be like having two, so you could do two samples at once could be a benefit.
Yes, so actually this allows, if I ignore the DSC mode, I can do a dual beam TGA mode. So if I want DSC data, I have to have an empty pan on the back one, but it is possible, dual sample TGA possible. So I have the ability potentially to double my throughput if I'm doing TGA only, not if I'm doing the DSC side.
Potentially get more accurate data because, I mean, you could run two of the exact same sample and then see what happens.
Oh, that's true. If you're doing the dual beam TGA, you can do two of the same thing. Absolutely. Another benefit is TGA, and actually I haven't drawn it yet, but like the graph is typically going to look something like this, where I have temperature or time on my x-axis, and I'll have mass either in a percent or in total milligrams. And my TGA line, I'll do TGA in blue. Might look something like this. And this is reminding me that we haven't talked about like how we analyze the data, so we'll do that after we talk about this combo instrument. And that would just be the output of a standalone TGA. I would have no idea whether those mass loss events are, you know, endotherms, exotherms, maybe something just like fell off the pan and there was actually no change whatsoever to the material itself, really. Having the additional DSC data, I think that's like a sparkly brush. That's some nonsense. Let's choose, I don't know, maybe we're sparkly. Oh, it's way too thick though. Whatever it is, we cannot be that size. I might have my DSC line showing me a peak here and nothing going on there, and then a peak here. So this would show me that in this mass loss event here had no heat flow change. And that would maybe tell us like something fell out of the pan, or maybe it was actually like a, I don't know, a multi-phase system and we didn't really like, not that much changed to it or anything. And then these little peaks would tell us whether that was an endotherm or an exotherm. Either of these graphs by themselves are fine, but when we look at them together, we can get a lot more information. So going back to, if I was just looking at the DSC, I'd be like, oh yeah, I have two, say, endotherms. I wouldn't have any idea that something had happened in this range from this line of data. What I've drawn here is not particularly, like, you're not gonna see a graph exactly like this very often, but it illustrates the point that by doing both at the same time, we are gaining quite a bit of insight into each other. So DSC and TGA support I don't really know how to put that. DSC and TGA, like, co-inform. So we are learning more about our material by doing both. And if I had to run a TGA test and then run a DSC test, assuming I have enough material to run both, so less material for 2 tests, and it's also faster than 2, oops.
So you can run a TGA alongside the DSC?
Yes, so we are collecting both the DSC and the TGA at the same time in this combo instrument, which means we're collecting twice as much data in the space of 1 scan instead of in the space of 2 scans.
So, yeah, which completely normalizes the data if you're considering it in terms of time. Because it's just like, oh yeah, this happened exactly at this point, and we know that because it was running off the same internal clock.
Exactly, yep. So there are quite a few pros to combo instruments. Some of the cons we talked about, like we have now complicated an already complicated instrument. Also cons, DSC likes 10 degrees per minute. TGA can go much faster. So we have to choose whether we're going to choose a speed that is beneficial to TGA or to DSC. TGA, I don't think there's a, like DSC, we just do 10 degrees per minute. That is across the board the recommended rate, unless you have a very good reason to change it. TGA, I don't think we have as set a speed. We're not like, this is always how TGA should be run. But 20 degrees per minute is more standard in a TGA run. So we have to choose one that's going to work for the other.
I'm assuming that you have to wait for heat to flow into the thermocouple to be able to sense it compared to, oh, you're just detecting mass, you can full throttle and we're taking 50 samples per second.
Yes,
100 samples per second.
there is definitely some consideration like thermodynamics and kinetics, and I talk through that in the DSC kind of explainer. But there's absolutely some considerations where DSC, if you're going too fast, kind of delays the onset of some things working. Like if I were to throw an ice cube into the oven, suddenly we have an ice cube existing at 400 degrees Fahrenheit. That's not thermodynamically stable, but if I'm watching it, like, yeah, I'd be like, oh yeah, ice doesn't melt until past 400 degrees Fahrenheit because I've just blasted it with heat really quickly. So that is absolutely a struggle with DSC. We have to go slow enough that allows the kinetics and the change to happen. TGA doesn't tend to have as many kinetics getting in the way for the mass loss. Once mass is freed, it's like, I'm out of here.
Sweet. Yeah, could you, like, if you know like a certain area, oh, the melting point's right around here, could you do like, hey, slow down right at this point because it's going to be super thermally active machine?
You absolutely could. DSC only collects well if you have a linear rate though. So any point where you're changing the rate, so let's say you were going 20 degrees per minute and then you slow down to 10 degrees per minute, in that minute or two while you're actually slowing the rate down, your DSC is going to be unusable. So DSC requires that linear rate. Typically the way we handle this is we just run at a speed throughout the whole thing. And we will either let it take a long time because we need the DSC, or we'll let it go faster because we don't care as much about the DSC. And there's kind of just the two sides to that. Other cons is mass recommendations. So I talked about earlier, 10 milligrams is about what we look for. But let's say I am looking at a 0.01% mass change, and I have 10 milligrams of sample, the total number of milligrams that I'm actually going to lose is going to be really, really tiny, right? If this is what I'm looking for in TGA, I would maybe say I need 100 milligrams of sample in my TGA in order to accurately measure to this level of precision. DSC, if I have too much material, it's like trying to melt an iceberg. It goes insanely slowly. So DSC needs about 10 milligrams of sample. TGA might need more than 10 milligrams. Again, in this case, we are just choosing, if we have to pit them against each other, we err on the side of the instrument, of the technique that we need the most. In some cases, we might find that it is better to run a good quality DSC scan and also a good quality TGA scan in two different instruments or in two different tests. We lose a little bit of this like time relational, nice pretty stuff.
If you're doing off temperature, then you're probably fine.
But as long as you normalize the temperature, it's probably fine. And if you use the same instrument, then it probably is gonna be okay. So those are some cons. Is DSC and TGA are not perfectly compatible. They're fine. And it's really useful to have them together in some situations. But anytime you use an instrument, it's worthwhile to know, does this work for me or does this work not for me? Not every instrument is going to work for every project. All right, with the last couple minutes, let's talk about reading the data. Meep. Oh, and I also want to talk about high res. We'll talk about that in just a second. So I've got data. I don't know why I did that last little bit. And just draw it to there. I'm remembering my x-axis is probably temperature, and my y-axis is probably like percent or milligrams. I have not drawn scale here, but let's say this is like 100 degrees Celsius-ish here. Really commonly, on almost every sample, there is a little bit of water that sample has absorbed out of the air. We live in Utah, so humidity is a minor problem to us, but is still a thing. Sometimes it rains every now and then. So very commonly, we're going to see water loss or dehydration right at the beginning, somewhere between 100 and 150 degrees Celsius. That would indicate whether it's like something hydrate. We can double check if that hydrate is as high or as low as it advertises. This might mean shelf stability. We can study things about shelf stability. This might indicate how successful our previous dehydration procedures were. If we're trying to dehydrate a material, I can then check, was I successful? If my x-axis is in time, I could also study how long does it take to dehydrate my material. So all of those kind of considerations. It's really common to see a little bit of water loss at the beginning of something unless it was very specifically kept dry. On this, what I can do is I can take this value here, and I can take this value here, and I can get the total percent change. And from that, I could go back all the way up at the top. I had that, like the H2O and the CO2 that come off of that baking soda, washing soda reaction. And I can see what percentage of water came off, what percentage of carbon dioxide came off. Okay, in this next region here, you can see I have a decrease there I have a decrease there, and I maybe even have a decrease there. So I think I have 3 mass changes all in very short order. And what's happened in the way that I've drawn this is this first, I'm gonna number the 1, 2, and 3. I know that H2O has already happened, but we're calling it number 1 there on the left. Probably what happened is number 1 didn't finish before we reached the temperature of number 2. And number 2 didn't finish before we reached the temperature of number 3. So to some degree, all 3 of these events are happening at the same time. We could, here, let's see, how are we gonna do this? We're gonna reactions often happen at similar temperatures. That blurs the onset and offset. That's the beginning and the end. To fix it, we can go slower. For example, running at 10 degrees per minute instead of 20 degrees per minute. We also can use something called high res. This is, I think, specific to TA instruments, but it's really cool technology. So high res, the instrument monitors mass change, and it controls the rate. Normal heating, I've got time, I've got temperature, I have a linear rate, right? So this one would be like 10 degrees per minute is the slope of that right there.
So it changes the amount that it's heating, and it's like, oh, I'm starting to see a mass loss. Let's keep at this temperature until that dips down and levels out, and then it says, oh, hey, now it's been flat for a while. Let's start increasing the temperature. Oop, there's another one.
Exactly.
Oop, there's another one.
So we get sort of what's called a quasi-isotherm. So it's heating at that 10 degrees per minute, and then it starts to see a mass loss. Right, my axes again. It starts to see this mass loss, and it will actually sort of hold temperature for a minute until that mass loss event is able to complete. Then it's going to speed back up toward 10 degrees, but it'll slow back down if it starts to see more mass loss. So in our case, where we had 3 mass loss events kind of all on top of each other, my time temperature graph is going to look a little bit more like this second one.
Which is a pain in the rear end if you're trying to get temperature normalization.
Yes. Also pain in the rear end if you're trying to do any sort of DSC, because DSC, like I said earlier, requires a constant rate. So let's see, this is...
I suppose it wouldn't be that terrible. You just say, oh, hey, this much mass loss, you just run 2 sets. One with linear, one with the high res.
Exactly. So this would be one of those situations where it's better to separate out DSC and TGA. High res is TGA only. You cannot run DSC at the same time as a high res scan. But it separates out these kind of very close together reactions very nicely. And then continuing on our graph, we get this final value. We obviously have like some big, like I think 3 probably continues all the way down to here based on what I'm seeing. And you can do any combination of derivatives on this line to make those peaks a little bit clearer. People will do first and second derivatives so you can really tell where the slope is changing between 1 and 2 and 3. And does 3 have does 3 continue here, or is there maybe another one in here?
Because it tells you concavity, and then you can say, oh, hey, it just starts being concave down at this point, not level.
Exactly. Yep. And then at the end, we would call this usually the residue. It's just whatever was left over in the pan at the end of the scan. That residue can be really useful, especially in like reactions where you're seeing maybe some weird byproduct and you're not expecting to see the weird byproduct. Knowing the mass of residue can be helpful in figuring out what that byproduct might be.
And can you do like analysis on the residue and see, oh, hey, what the crap even happened? Like,
Yes,
oh,
so
there's two more reactions that are occurring. What is actually here?
You could take that residue and you could turn that into, you could like run electron microscopy on it, you could run FTIR on it, you could run XRD on it, you could run more TGA if you want to go to a higher temperature. So yeah, you absolutely can kind of recover that residue. Remembering we're only working with probably about 10 milligrams here.
Yeah.
So you maybe would want to run, like create your residue in a furnace rather than in the TGA. But you absolutely can take this and run with it if you want. A lot of people will do, did I talk about evolved gas analysis?
Yes.
I feel like I did. There is another addition, so you could make a triplet instrument that also analyzes the gas flowing out of the furnace to tell you exactly what's water, what's carbon dioxide, etc. That's called evolved gas analysis. We don't have that, but we would really like to have that in our lab. So it's been something we're working toward a little bit.
Burning holes in people's pockets.
Yeah. Yes, just trying to find where the money is. Nowhere in academia right now.
Yep.
But there are systems that can measure the gas coming off the back of that, so you can get yet a third line. It'd be like carbon coming off the furnace at any given time, and you could measure that along this axis as well. So lots of really cool things, and it's why there's a benefit to having this sideways setup